So we were doing piece by piece, checking the symbolic derivatives and the numerical derivatives would match. It looks like what I did last time is the difference loss NP loss substituted. So loss NP is cross entropy loss. Loss substituted is loss, but I'm not doing a derivative here or anything. Huh? Why I was even doing this? Why I was even I mean, I was just checking that. This is not checking that the derivatives are the same. This is just checking that the functions are the same. Let's try to. So you have the loss function here, which basically it's a function of the, and that's a symbolic one. Yeah. And where is actually the loss NP? Okay, here. Sum of. Yeah, okay. I was trying to. I think what I was trying to do is I was trying to make sure that at least the numerical function representations were the same as the symbolic ones, which in this case they are, right? Because the results are the same. So the label is just wrong. These are not derivatives. So the loss function, right? It's the well, essentially, it's a function of y true and y prime, right? The predicted and the true labels. Now. That's all good, but it's essentially, what are we even doing here? So this is the forward pass, and I think we're trying to calculate. So we're trying to calculate the derivative. We're trying to back propagate. So we're trying to back propagate across the stuff that needs to be modified, right? Like W2, for example, and W1. So Z2 and then Y pred, basically the predictive values is softmax. Here's softmax. That's what we should go and check now. Do we need to? So do we need? What do we do with softmax? Do we need to? We also need to do the derivative of these, right? Softmax NP is here. I don't know. Did I test that? What did I test last time? So if I go here. There's too much. Think. Y pred. Oh, I was not even using it later. Okay, that's fine. I think I just started with a loss function, and then I was supposed to kind of go backwards to that. Loss is the same. Loss is correct. Now, it's funny how it was just like a month difference, how much you forget. That's what's very hard about this kind of stuff, the continuity. So we've got the loss function. I'm really not thinking well. So we have the loss function. That's sort of our starting point. True values, and then we want to calculate. We want to do the derivative. So we want to do the derivative of each of the elements that we want to be able to modify with respect to this loss function, right? With respect to the loss function. Loss substituted, so originally the Z2, that's what we want to do first, right? Because essentially, why are we doing these? Why do we need to kind of chain it back? I mean, it's the derivative with respect, again, think first principles. Is the derivative of W2. The derivative sometimes is, I think too much. I just tend to think too much, sort of from some kind of prescripted process perspective. So let's think first principle. So we have W2. That's what we want to do, right? W2 what does W2 depend on? What does W2 depend on? I mean, W2 is just W2 is just a matrix, right? W2 is just a matrix. The derivative of W2, derivative of Z2. Softmax inputs, the derivative of Z2 of Z2 of Z2 of Z2 of Z2. You want to, so again, what you're optimizing is the loss function, right? So you want the loss function to be minimized. That's just the traditional mathematical optimization problem. In order to optimize, you wanna essentially, what you wanna do is you wanna do the derivative, because the derivative tells you then how is that function then evolving, right? What is the rate of change? How is this function changing? And so then then you would know kind of where to go, sort of how to modify oh wow, I'm just having a blank moment. I'm just having a very big blank moment. Just having a very big blank moment. Essentially, this is my forward pass. These are my inputs, right? My input is X, right? This is my input is X. It helps to just sometimes just go back to the basic maths, right? So ignore even they are matrices. This is just, and these are constants, right? So these things are constants. So this is your input. So you want to just modify these things in here, right? So that the loss function is kind of like optimal. now the loss function depends on essentially z2, right? I mean, after not even that, like it's these, right? So this is really, this is your prediction. This is what you have in here. Sorry. So the what you're trying to do, you're trying to say, so this is my predicted value, so then this I have my loss function. So in order to find this is stupid. This feels very stupid. This is gonna be 30 minutes of me looking at the screen and feeling stupid. Really to get some more sleep, I think. So essentially what you're trying to do is to try to calculate the derivative. This is a function that essentially, sort of y true, well, essentially you can, it's a composite of all these, right? So you're going to end up with x in there at some point, right? So when you're calculating the derivative at a certain point, what you're getting is sort of a number or a vector that sort of tells you in sort of which direction, right, the function is. Like, what's the inclination, right? Like in stupid terms, you know what I mean? It's like if you've got some kind of curve like that, then you're gonna get like that. When you go to the limit, you're gonna get this kind of like tangent in there. And so you're gonna get that inclination value of that. So and this is what you're looking for, because this is the number that this is sort of, it's a quantity that you can use to modify your original input, because you know that if you modify your original input, that, like, following that direction, then you're going to get like a lower value of the actual function, right? That's why you want the derivative. That's what the derivative is at that point that you're right now, and that point that you're right now is what you've predicted, is y pred, right? So, and that's the function well, it's y pred. It's the point you're right now is the value of is x, is these, right? So y pred is just a function that calculates you that, but the point your input is x, right? So, but now you wanna, the trick here is what you have to treat as what you have to think of is I have a mental clash with just saying the derivative of W2, because this is a constant. You know what I mean? I think the problem that I'm having is just purely at the definition level. What is the function? What is the variable? What is what in all this mess? Because things are then matrices and and it just makes it it's easy to state the statement. It's easy to just like intuitively it makes sense, but peel off that intuition is what's and sort of understand the true nature of what's going on. It's like this is what kind of this really feels like that's the training that the brain needs, right? So you have the because essentially here what we're doing here is like the derivative. So the derivative of W2. That's not the derivative, it's the delta. That's kind of like, that's what you want. That's the delta of the delta you have to apply to W2, right? This feels really stupid. You can't imagine how stupid this feels. You really can't imagine how stupid this feels right now. I have the loss function, right? What am I even doing? Respect to W2. Is it that we're treating W2 as a variable now? It seems so. It seems so. I think that's theoretically what we're doing, right? We're treating W2 as the as an actual variable, right? Because we don't want to move these. That's a thing. That's a thing where another mix-up is happening. So the reality is that's what you have. That's your input, right? But like that's not what you want to modify. That's what we're trying to modify is these. So these are your variables, right? So these are your variables actually. That is the biggest issue here. I'll come back to this in a second. I'll have to kind of hop off and on for a call now. But this is so. W2 is really what the variable is, exactly, and we treat everything else as a constant, and so that's why we're doing these. I don't know what it's funny. I don't know what is it that makes my brain think this way, or make these mistakes. You know what I mean? It's like I keep doing this repeatedly. It's like I start from the beginning. I sort of like start from scratch thinking about the problem, right? And I'm like, what am I even doing here? And then I'm like, I'm just making this kind of mental journey all over again sometimes, where it's like, okay, this is my variable, and then I'm like realizing, no, that's not my variable, this is my variable. That's why that's really at the crux of like what you're trying to solve here. It's a very important. It's very important to understand what is it that you're trying to solve, what the actual problem is that you're trying to solve, rather than like just like following instructions. Or it's like, oh yeah, it needs to be the derivative of this. We need to calculate like you know what I mean? It's for the first principles thinking to work, you really need to understand what is it that you're trying to solve. Like if not, you're not truly understanding the problem, right? You really need to understand that. It just feels like a stupid obsession, or sometimes even like a waste of time. But it's very valuable exercise for your brain, right? What is it that we're trying to do? Sort of what are the here's we've got a loss function. This loss function is just basically a function of two things. It's a function of an expression that tells. It's a function of an sort of a truth value, and then an expression that calculates a predicted value, right? and it's a function that basically tells how similar these two things are. So you want to minimize this function. That's fine. That's a first step. That's mentally okay. In order to do that, you need, in order to do these, what are the things that you're tweaking into these functions, right? To do that, what are your variables, so to say? Because it's like you're just like kind of moving knobs, you know, like you're just like tweaking little things here and there and seeing how it changes. And so essentially that's why you want to do that derivative, so that you know how much you need to move something. Now the beauty of this is that you can, which is not trivial either, like the fact that if you have multiple variables, you can just treat them independently. That's also something that is not very trivial, right? It's not something, I don't know, that I would naturally kind of assume and like say, oh yeah, it just makes sense intuitively. I don't know, maybe something like another rabbit hole to dig into at some point. But it's like then you have that thing where it's like, okay, now I wanna touch these, right? So you kind of change your whole expression, right? And that's the stuff that I'm trying to move away from. It's just basically saying, okay, that's all. So I want to use symbolic. I want to use SymPy to just say, like, if I have that, that's all I want to do, right? So that's why here I'm just basically saying these are the symbols, right? It's all symbolical. So these are the symbols. And when we're doing substitutions, maybe that's the problem. Maybe that's the problem. Why am I substituting W2? Maybe that's the problem. Maybe that's the fucking problem. Because that's what you don't want to substitute, right? Why am I substituting these? What does that even mean? That's what you don't want to do, right? So you want to, okay, so let's, and I think what we're trying to do is we're trying to keep softmax out of the picture, but let's try to put softmax back into the picture. So we have this function Z2. We have softmax. So we've got softmax, we've got ypred, and then we've got the loss function. That's all good. Computer symbolic. Okay, so here's, thanks God I was just basically, can I get out of history mode? Thanks God I was just, oh no, thanks not God. Well, yeah, I think I was just commenting the stuff. So yeah, okay. The derivative of the loss with respect to W2. Oh yeah, no, but I'm of course. No, these substitutions are good because they are needed for the evaluation with respect to W2. And how do I know these? It's doing what I wanted to do. Can I just? Okay, can I just stop here, right? So essentially, this is what we're doing. We're telling it, just tell me, you know, this is the variable, and tell me the difference. Like, it's funny. Oh, it's funny. How can I? Okay, so can I just comment all that part in here? Well, I think I just have to do. I think that was the way to do it. Yeah. Can I just leave it like this? Is it gonna complain? Yeah, I think I need to put the end here. Oh, I hate the autocomplete in this case. Okay. I'll go back to this today. I'll go back to this later today. So this is not going to be the latest video. Okay, so, but see, maybe a problem that I'm having here is that I would simplify things a lot if before doing these I would actually do a replacement. I would actually do a let's say we initialize all these earlier, right? So this is the, so we do this here together. Okay, so this is the NP stuff. I have to clean that code, is fucking shit, man. And then I do, let's say, a substitution, the thing here, right? Before, like, let's before the derivative. And then what I do is I don't substitute now the W2 stuff, okay? W2 stays like not substituted, so everything else is substituted. What do I get now? Is it gonna work? Is it gonna work? That's my first question. Yeah, but that's not what I want to get. Console. What the fuck? Run. That's what I want to see what happens here. No, wait, stop. I haven't I haven't done the substitution. So I should do the substitution first before the derivative. Before. So, okay. So loss substituted. Stop this shit. So this dictionary, this is the function, and then what I'm differentiating is these now. Okay, let's see. Give me a second, guys. While this is going on, I have to write a quick message. Okay, actually, it doesn't look that bad. Is it really? Can I simplify this now? AI. How to simplify an expression in SymPy? Simplify. Just simplify. Can I just use simplify? Because now it's much easier, right? This is something I didn't do before. Simplify. SP simplify. Well, I can use div directly. Yeah, okay. That's stupid. Let's see what I get. Here, down here. That's. Can I just? That's what we're looking at here at the bottom. Simplify is actually, I think, might be a little too heavy. Because the thing is, you know, like you could even use these to just like programmatically say, now I have a simple expression, that's my derivative. So can you turn a SymPy expression into Python code programmatically? That would be cool, because then, I mean, Lambdify. Yeah, so there is actually Lambdify. Something we could try. Interesting. Okay, guys, I'll come back to it later. As I said, I'm just gonna stop the video now. We'll upload this, but then I'll kind of come back to this later. Okay, come back to this later.